For more physics-related videos, please subscribe. In this video, we're going to be looking at projectile motion problems that involve finding initial conditions. I've rated the physics level in this video as easiest. Like all projectile motion problems, we're going to start off with our three kinematics equations. If you'd like to know where these equations come from, you can watch my video, Projectile Motion Made Easy. Initial condition problems are projectile motion problems in which you're asked to find the starting condition of that projectile. So that could involve four possible variables: the initial height, or the y position, the initial horizontal position, or the initial x position, and the initial velocity, which has two components, the x velocity, or the horizontal velocity, and the vertical velocity, the y velocity. Generally speaking, it's pretty rare to come across a problem where the initial x position is not zero. So really in practice, it's going to be one of three variables. One thing you should be aware of for initial condition problems is that there are often two solutions, so watch out for that. Now, the best way to understand something is to simply practice it, so let's do an example. In this example, Tom Brady aims to throw to a wide receiver 50 yards away. If he can throw at 60 miles an hour, and assuming the ball will be caught at the same height as it was released, at what angle must he throw the ball for it to arrive in the least amount of time? Since we're not using metric units in this problem, we can take g, the acceleration due to gravity, as 32 feet per second squared. In a previous video, I covered the 5 easy steps to solve any projectile motion problem. So that's what we're going to follow here. If you'd like a more detailed explanation of these 5 steps, you can check out that video. Step 1 is to draw the situation. So in this case, let's start off by drawing the ground, and we're going to have a ball thrown that's going to follow a parabolic trajectory. The ball is thrown with some initial velocity v0, which is a vector, and it's thrown at an angle theta. The range, meaning how far the ball travels in the horizontal position, we're going to call delta x. And in this problem, we're told that the height at which the ball is thrown is equal to the height at which it's caught. Even though that's technically not the ground, we can just call that the ground, and it's actually not going to change anything mathematically. The next step is to write down what we know and don't know, keeping in mind that there are a total of 5 variables in every projectile motion problem. First, we're told that the initial velocity is 60 miles an hour, which I'm going to immediately convert to 88 feet per second. We're also told that the ball will travel a total of 150 feet in the horizontal direction. We don't know the angle at which the ball is thrown at, nor do we know the time at which the ball is caught. And remember that velocity is a vector. It has an x component and a y component. Given the angle the ball is thrown at above the horizontal, which we're calling theta, we can write the x and y components as v0 cosine theta and v0 sine theta. And notice that I've specified v0 y for the initial y velocity because it changes with time, whereas the x velocity is the same throughout, so I don't need to specify it as the initial x velocity. It's just the x velocity at all times. If you're finding this video helpful so far, please like and subscribe, maybe share it with your classmates and friends. In this step, it's also useful to ask, is this a when question or a where question? In this particular question, it's not so obvious, but this is actually a where question, and that's because we're not given any information about time, nor are we asked anything about time. Since this is a where problem, this means we're going to have to eliminate time from our kinematics equations. And finally, we want to define where our height is equal to 0. In this problem, I'm going to call the initial height y equals 0. The next step is to write down what is being asked in this question, and are we dealing with one of the 3 special points. Most projectile motion problems will involve one of these 3 points, although they don't have to. In this case, we're dealing with the initial point. Now, what are we being asked to find in this problem? We're being asked to find the angle at which the ball is thrown. We can now move on to the next step and write down our kinematics equations, keeping in mind that we have to separate the x and y directions. We have 1 equation for the x motion and 2 for the y motion. Make sure you use the appropriate equations for the appropriate direction. If you mix them up, you're going to get the wrong answer. We can now move forward and solve these equations, making sure we don't plug in any numbers until the very last step, unless that number is 0. If you know that a quantity is 0, plug that in right away. Otherwise, do not plug in any numbers until you get an equation of the form, the thing we're looking for equals a bunch of stuff we already know. So, Let's start with the x equation. For this equation, we can solve for the time at which the ball is caught. You may be tempted here to plug in some numbers. Do not do this. Remember step 5, do not plug in any numbers until you have an equation of the form the thing we want equals a bunch of stuff we already know. In this case, time is not what we're looking for. We're looking for theta. So keep everything in terms of variables. Now that we have expression for the time, let's just keep that in our back pocket and move on to the y motion. We're told that the ball is caught at the same height at which it's thrown. That means that delta y, our change in y position, is 0. Since both these terms on the right hand side have a factor of t, we can eliminate one factor of t, and we can now substitute in our expression for the time at which the ball is caught. Now remember, we're solving for theta, so I'm going to rearrange this equation to have every term including theta on the left hand side of the equation and everything else on the right hand side. At this point, it's useful to know the identity that 2 sine theta cosine theta is equal to sine 2 theta. You can still solve this without knowing this identity. You'll have to convert cosine theta into the square root of 1 minus sine theta squared. This comes from sine theta squared plus cosine theta squared equals 1, but it's going to be a little more difficult. So it's useful to know this identity. Now, in order to get theta out of the sine function, we apply the sine inverse function to both sides. And at this point, you need to be careful. Here, you might think that this is the solution to theta. But remember what I said in the beginning, look out for 2 solutions. So let's draw the trigonometric unit circle with a vector pointing at an angle 2 theta. Now, sine of 2 theta is the vertical component of this vector. However, this is not the only angle that will have the same value for sine. The mirror image of this vector about the y-axis will also have the same value of sine, meaning it has the same vertical component. So both of these are possible solutions. However, the inverse sine function only knows about the first and fourth quadrants. It does not know about angles in the second and third quadrants, so you have to look out for this. Now we have to be consistent and make sure we measure our angles always from the same spot, which I'm going to measure from the positive x-axis. This means that our second solution will be 180 degrees minus our first solution. Both of these angles are possible solutions. Now we have 2 expressions of the form, the thing we want equals a bunch of stuff we already know. We just have to divide by 2 because we don't want 2 theta, we want theta. So dividing by 2 and plugging in our numbers gives us theta equals 19 degrees or 71 degrees. At this point, we can go back to our original question and see that it's asking us for the solution that gives the ball arriving in the least amount of time. This will be the smaller angle. The larger angle will be more of a lob. It'll take a little more time to get the receiver. So the solution to this problem is 19 degrees. There you go. That's how you solve an initial conditions problem. But remember, initial condition problems don't always ask for the angle. They could also be asking for the initial speed or the initial height, and possibly the initial x position, but that's pretty rare. Generally, you can always set the initial x position to 0. If you enjoyed this video, be sure to like and subscribe. In the next video, we will be taking a look at what throwing angle maximizes the range. So if you'd like to see this video or more physics videos in general, be sure to hit the bell to be notified for the release of future physics videos. Thanks for watching, and I'll see you in the next one.